Well, thank you, Nahir, for the introduction. And before I start, I want to thank Ivona and Nahir for inviting me to this talk. I'm very excited to see so many indentation experts all at once. And to contribute to this workshop, I will tell you indentation, it can be a simple and robust method to characterize the poroelasticity of gels. So you heard a lot from Michelle's talk this morning. It's very fascinating, and I will talk more from the theoretical point of view through this talk. Well, this work was done a couple of years ago when I was a PhD student working with Professor Zhigang Suo and used Viscoelastic at Harvard. So let's first take a look at what poroelastic material is. I saw some students there, maybe they don't know these concepts. So poroelastic material are two-phase materials composed of both solid and liquid. So the so-called poroelasticity was originally developed for solute material by Tazagi, and later on it was, this theory was generalized by Biot, James Rice, and a few other scholars. Well, so lately this theory was also started to be used on biological materials like bones, and a lot of people in this workshop presented their important works on bones, especially Michelle also did some work on bones in the perspective of poroelasticity, right? So today I'm going to tell you gel is also a type of poroelastic material. It's composed of polymer chains and solvent molecule. So if you think it as a material, it's both the solid-like and the liquid-like. The polymer chains are cross-linked by a strong bond, so it can retain shape and bear load, right? So on the other hand, the gel is also liquid-like. Comparatively, the bonds between the polymer chains and the solvent molecules are relatively weak, so the solvent can transport through the network. And the gels are almost everywhere in our daily life, right? From the food that we eat and the things that we use. Well, gels are important nature materials. For example, this cartilage is a gel. It's soft, slippery. It provides small friction between bones. Well, this cornea is also a gel. It's transparent, soft, and permeable to water, oxygen, and nutrients. Well, besides animals, the plant also use gels. For example, this peptin gel here, it can swell or shrink in response to the pH value or salt concentration of the surrounding liquid. So in this way, the plant can regulate hydraulic pressure and flow inside the vessel. Well, gels are also important engineering materials. A lot of the gel can be made stimuli responsive. So here is one inspiring work done by Professor David Beebe at Wisconsin Medicine. They fabricated this gel post inside a microfluidic device. Well, in response to the pH value of the surrounding liquid, this gel post can swell or shrink. So the channel is opened and closed accordingly, right? So it's a kind of a smart valve. Well, gels can also be engineered to resemble the extracellular environment. So that enable their use in many biomedical applications, such as drug delivery and tissue culture scaffolds. Well, in larger length scale, gel is also used in large-scale engineering field. For example, here, people use these swallowable elastomers, or called swallowable packer, to seal the oil well. Well, so in all these applications and many other applications, the important questions that people usually ask are the following: how large the force it generates, and how long it takes to respond? Well, in order to answer these questions, and in order to have a good control in material design and structure design, we need to characterize the mechanical and transport property of the material quantitatively, right? So, but mechanical testing on soft materials are not trivial. And Michelle, in her book, she can tell you a lot of reasons, right? You need to use indentation. Here, I just want to say a few words. Well, most gels are very soft. Some of them are slippery and brittle. Well, so the traditional method like tension, bending, or torsion are very difficult to be applied on gels. Think about jello and tofu you eat. So it's very difficult to do this type of measurement. But comparatively, indentation is very simple. You just have this sample, and you press the indenter into the gel. Then you can back out the material property. It requires minimum specimen preparation, can probe local properties, can perform several times on a single specimen, and most importantly, you can easily probe the material into different length scales. You heard a lot from Virginia's talk and many other people's talk here. So the real difficulty for using indentation is really from the theoretical aspect. It is a very complicated boundary value problem to solve. It's a mixed boundary value problem, especially when you talk about time-dependent behavior of the gel. Within the contact area, it's a displacement boundary. Outside of the contact area is stress-free. And also within this contact area, you don't have liquid transport through this surface, but outside it can transport the liquid. So it's very difficult to solve, right? So the difficulty for using indentation has long been how to relate the data you get from indentation measurement to the material properties. So this study is aiming to solve this problem, right? So in order to define quantities, we recall linear poroelasticity, which was developed by Tazagi, Biot, and James Rice, and many other peoples. Well, in order to adapt poroelasticity to gels, there are two important considerations. Well, we get that a lot. Gel is soft. It usually generates a large deformation. Can you really use linear poroelasticity to model the material? Well, the answer is yes. The rationale is the following. Gel usually can absorb a large amount of solvent and have huge volume change. But the indentation that we introduced is after the gel swell to a certain state, and we maintain that state. Then we do this indentation. It's like you compress the elastic material, right? You use Hertzing solution a lot. It's the same here. You can still use linear poroelasticity. The second consideration is, as I told you, gel is very soft. So the stress it can sustain is usually small. So under this stress, you can't compress the individual solvent molecules or polymer chains. So the individual polymer chain and solvent molecules can be viewed as incompressible. So the volume change of the material is solely due to the change of solvent content. All right, so let's take a material element. There are two ways of doing work to this material element. One is applying a load. The other is by pumping molecules into the material. Mu is the chemical potential. C is the concentration of solvent molecules. But here, because we have an assumption that the volume change is entirely due to the change of solvent concentration, so this volume change, epsilon, the string, is related to solvent concentration. Now, the free energy of the material element is a function of string only. And for linear material, we know this W is a function of, is quadratic in string. And for isotropic material, W is a function of invariance. And here we only have two invariants. When recall your solid mechanics class, there are two invariants. One is epsilon ij, the other is epsilon kk, right? So we only need two parameters to represent this free energy function. If you write it in this way, these two parameters are shear modulus and Poisson's ratio. And now let's take a gel body. Well, still the kinematics is small deformation, and the governing equation we have force balance. And because we have mass transport inside the material, so we have mass conservation. And the flux is driven by chemical potential gradient. Here we adapt Darcy's law, but it's not necessary. You can see here, if we derive this mass conservation in terms of solvent concentration C, it's just a simple diffusion equation. You can put a parameter D here. It's a phenomenological parameter. We don't input, give any kinetic model. But if you talk about Darcy's law, you already imply a kinetic model. Yes?
What is omega called?
Oh, sorry. Omega is the volume, where is it? Omega is the volume of one single solvent molecule. So you time this omega with the concentration of, the concentration is defined as the number of solvent molecules per unit volume of the material, right? So, so this is a phenomenological parameter. We don't give any kinetic model. So if you say it's Darcy's law, you already imply it's a pipe flow, right? But it can also be self-diffusion. But here I just want to tell you this is an effective number that we measure later. If you believe in Darcy's law for this material, the expression is the following. K is the so-called permeability. It scales with length squared. So for gels, it's the mesh size squared, right? Eta is the viscosity of the solvent. So in order to characterize the material, we have three parameters to characterize. Here, let me put a few words about this Poisson's ratio. So for linear elastic material, you know it's you pull the material in lateral direction and you count how much contraction you get in a transverse direction, right? So, but Poisson's ratio for poroelastic material is different. It is the following. You pull the material in lateral direction. Because this pulling, you increase the chemical potential inside the material. The solvent doesn't feel comfortable. They want to move out, right? Then you hold your displacement there and wait until the solvent migration reaches equilibrium. Then you measure how much contraction you get in other direction. This is the Poisson's ratio for poroelastic material. If you like, you can view it as equilibrium Poisson's ratio. But actually, the material is just fully characterized by shear modulus and this equilibrium Poisson's ratio. And the time-dependent behavior depends on geometry. Well, how do we characterize this material? We first put the gel into solution until it is fully swollen. Then we press the indenter into the gel to a certain depth and measure the relaxation force. There is a very important theoretical point for us to do relaxation test rather than creep test. I will come back to this point later. But here, from the measured force relaxation function, a curve, you can get three information: instantaneous force, equilibrium force, and the time it needs to reach equilibrium. So three features are enough for us to definitively characterize the three parameters. You don't need to do curve fitting. Let me tell you how do you do that. Well, remember, right after the indenter is pressed into the gel, solvent molecules don't have enough time to migrate. So instantaneously, the material really behaves like an incompressible linear elastic material, right? And we can use this Hertzin solution. Take a spherical indenter as an example. You can use this Hertzin solution, substitute the instantaneous force into this equation, and set Poisson's ratio equals 1/2. You can directly calculate shear modulus. Well, if you wait long enough, the solvent will migrate out of the gel because the compression make it uncomfortable. You increase the chemical potential gradient, so the solvent will migrate out. So until the equilibrium state, the material behaves like a compressible linear elastic material. So we can use this Hertzin solution again, insert this equilibrium force into this equation, and now you know shear modulus. Then you can directly calculate Poisson's ratio. Right? You have question?
Yeah, I did. So why doesn't the fluid, you talked about the difficulty of solving the problem with all these mixed boundary conditions and the fact that fluid can flow out outside of the
material, yes.
Why doesn't it flow out immediately when you indent? So you can't even use Hertz.
That's because of when you press the material, it's not like a form that the liquid can flow out relatively fast. But even it's fast, it still needs time, right? But for gels, it's very significant. It's because the formation of a gel is mostly entropy dominant. I will come back to this point in detail later. So this osmotic pressure really wants to hold the liquid inside. It's not like a foam. Foam is capillary force, right? You can squeeze liquid out easily, but here it's not. You really have to wait a long enough time for it to migrate out. All right, so that's a very good question. So now we know G and mu. The question is about diffusivity. How do you get this information, right? So let's come back to this relaxation test point. So if you are familiar with the Hertzin solution, the contact radius equals the square root RH. It purely depends on geometry, right? So educated guessing is during your relaxation test, if you hold your displacement, your contact area doesn't change. Why do we care about it? The reason is if you have a constant contact area, that means you have a constant diffusion length. Then the time becomes simple. The scaling becomes simpler. So the time will depend on the contact radius squared because it's a diffusion process. And I did a finite element calculation. I proved this is exactly the case. And most importantly, I proved if you normalize the force in this form, it's just rescale the force relaxation function from 0 to 1. Then this force relaxation function is a function of non-dimensionalized time, dt over a squared only. It doesn't depend on any other non-dimensional quantities, not even Poisson's ratio, right? That means each curve here is a master curve. It only depends on the shape of indenter that you use, right? That's a very important conclusion. That means this curve is a master curve. And this was derived by using finite element calculation. It's not an explicit expression. But because it's a master curve, I can just do curve fitting to get an explicit expression for other people to use. And that's what I did. So for several shape of indenter, this G tau function is summarized here. So from now on, people don't have to do numerical calculation anymore. They can just do one test and fit their curve to this G tau function. They can get diffusivity, right? And so you can do experiment. But before doing experiment, there is one important point you need to consider. right? Michelle talked about it a lot in today's talk, but because it's a very important point and concept, I want to emphasize it here again. So the time-dependent behavior of gel could be viscoelastic or poroelastic, right? So the question is, how do you differentiate these two time scales? The idea is very simple. So let's consider this relaxation test. If the time-dependent behavior is viscoelastic, the relaxation time is independent of the size of indentation. You will get the same curve, right, for different size of indentation. But if the time-dependent behavior is poroelastic, the relaxation time scales with contact radius squared. For larger size of indentation, the relaxation time is longer. Right? So there are actually two ways to differentiate these two time scales. One way is you use very large indentation size and wait and observe this relaxation phenomena for a long time. Then the viscoelastic happens very, very fast in the very beginning. The subsequent long time observation is due to poroelastic effect, right? There is another way that you use very, very small indenter. So the transport happens very, very fast. But you just focus your observation in the very beginning, right? You can still capture a poroelastic effect. And you don't care about later on the viscoelastic relaxation, right? So to prove concept, I first did a large scale indentation on a piece of alginate gel. And I did a very large size of indentation in order to make sure that I don't couple these two effects. I did indentation depths from 1 millimeter to 3 millimeter. And you can see the relaxation takes hours. So I first normalized this force time curve by normalizing force by AH. A is contact radius, H is indentation depth. This scales as stress. So you can see clearly these three curves separate. And for larger size of indentation, the relaxation time is longer. It's an indication of size dependent, right? Then I further normalized the time t by a squared. A is contact radius. These three curves collapse into one single curve. It's exactly the scaling for poroelastic behavior. Then we can safely use our method to get shear modulus from instantaneous force and Poisson's ratio from equilibrium force, and fit these three curves to this master curve. You can get diffusivity. It's very simple, right? And a lot of people are interested in doing things in small scale, and also that for some biomedical application, you can't do experiment just for hours just to get one curve. That's not possible, right? So, but if you can reduce the size of indentation, you will significantly reduce the time for measurement, because the time scales with contact radius squared, right? So I first, to prove this concept, I first did large scale indentation on polyacrylamide gel. This is our measured curve. And by collaborating with Professor Van Vliet's group at MIT, we conducted this small scale indentation by using AFM. And here the probe I use is 1 centimeter radius, and indentation depth from 100 to 400 micron is very big. And in small scale, we use spherical tip, 20 macron size, and indentation depths are from 4 macron to 8 macron. And you can see the time is significantly reduced from several hours to just several seconds. Right? But in both scale, you see poroelastic behavior. And the extracted material properties compared reasonably well, right? So Then come back to this nonlinear theory. A lot of people are interested in developing nonlinear theory for soft materials, and they may want to know that how our theory can help them. If we get a shear modulus, Poisson's ratio, how can they use it? Or whether they can use it at all, right? So here, let me, okay. I think I missed one slide. But the process of forming gel is mostly entropy dominant. So you have polymer chains and solvent molecules. The solvent molecules want to mix with a polymer network in order to maximize the entropy of the system. But meanwhile, the polymer chains are straightened. So the entropy also decreases, right? So the computation of these two effects will give you an equilibrium state. And the Fleury-Huggins, sorry, I don't know where that slide is, but Fleury-Huggins, who got a Nobel Prize for developing this theory, he said the free energy of the gel is a combination of stretching energy, stretching of the polymer chains, and mixing energy due to mixing of solvent molecules with polymer chains. Right, and he developed this thermodynamic model and using statistical skills to get this expression. And that's where this nonlinear theory in solid mechanics was based on. They used that thermodynamic expression to get nonlinear theory. So if you take a look at that nonlinear theory, there are essentially two parameters, n chi and lambda naught. Lambda naught is swelling ratio of free swollen gel. And n is the number of chains per unit volume of a dry polymer. It's related to cross-link density. And chi is the so-called Fleury-Huggins parameter. It describes the enthalpy of mixing, how much heat it absorbs or generates when you mix two things together. It's a chemical term, right? So what I did is I did a linear perturbation around the state of a swollen state. Then I compare nonlinear theory, linearized the nonlinear theory with linear poroelasticity. Then you can get these three simple equations. Now, for given shear modulus and Poisson's ratio, I can calculate n chi and lambda naught for you. Right? So here is the experimental result. I did an indentation on PDMS swollen in various organic solvent. So I measured the shear modulus and the Poisson's ratio for each system. And from the previous equation here, I can calculate n chi and lambda naught for each system. These blue columns are calculated value. Actually, they can compare with independent measurement. For example, this is our calculated value from measured shear modulus and Poisson's ratio. This is independently measured swelling ratio. It's simple. I just throw it into the solvent and measure how much volume it change, right? This is the measured value, calculated value. You can see very good comparison. And NKT is actually the shear modulus of dry polymers before it swells in any organic solvent, right? So for PDMS, I also measure this shear modulus independently before I throw it into organic solvent. And here is the measured value. Here is the calculated value. And you can do the comparison. But most interesting part is chi. Chi is, remember, describes the enthalpy of mixing. It's a chemical term. So in literature, people have various ways of doing this measurement. And this is a literature reported value. And surprisingly, our calculated value from mechanical testing, this value is very close to literature reported value. So now if you like to use the nonlinear theory, no problem. You measure your material using my method to get a shear modulus, Poisson's ratio, and you can calculate these parameters for your nonlinear theory.
Do you know easily the n parameters? So, I mean, why measure the shear modulus if you can just...
Yeah, you can.
NKT, I mean, how well
Yes.
do you know n?
So N is very difficult to measure. For PDMS, it's okay. It's still rubbery state when before you swell it in liquid, right? But for other like normal hydrogels, you can't do that. If it's dried, it's in glassy state. It's even before it totally dried, your sample will break into pieces, right? You can't do that, right? PDMS is this is, I would say, the reason I chose PDMS is because it's a well-studied kind of a model material system. I can do comparison, but material characterization-wise, it's not very interesting. This material is not that difficult to characterize, but for hydrogels, it's difficult, right? And I just want to say a few words. We also developed this theory with the consideration of film thickness, because sometimes you can't make your sample thick, right? So we found from numerical simulation when the contact radius is 10 times larger than the film thickness, you can use my previous presented theory. And for when the contact radius is 1.5 times larger than the film thickness, I actually derived the analytical solution for this extreme case. And you can find that solution in our paper. And in the intermediate state, this classical dependence will become depending on another parameter, which is square root RH over D. Essentially the contact radius to the film thickness. We have the full solution for this intermediate case as well. So this problem, I think, is fully solved now. So I want to thank my PhD advisor Zhigang So and used Velastic at Harvard. And later I went to Joanna Eisenberg's group to study some bio-inspired material. And I also want to thank Professor James Ress, John Hutchinson, George Wessels, Mahadevan, and Christine Van Vliet for their guidance and fruitful suggestions through my PhD study. And I also want to thank my collaborators, Xuanhe Zhao, Xin Chen, Taxin, Xiyao, and others. Now they all become assistant professors here, and they are all scientists in the company. So I'm very grateful to have them around me. So that's it.
In your indentation, the test, have you ever, not test simulations, have you ever observed bulging of the material? Because when you do it so fast, it's like incompressible material should bulge out. Have you ever captured such thing?
No, I don't think so. I think, like I said, the material mostly behave like elastic material. The bulge up, are you talking about like a plastic deformation?
The volume has to, I mean,
It's
if it
like-
goes down, it has to go up too.
Yeah, it's like when you
If it
press
depends
so
on the
fast,
Poisson's ratio.
you are compressing, and there's a compaction, and also there should be like, especially if it is not fully infinite domain.
From a larger scale measurement, I never see that phenomenon, but in small scale, I don't know. I can't observe it. I can't see the sample. But in larger scale, like in
simulation,
simulation, no.
why you didn't observe such thing?
Why do I observe it? It's a infinitely large sample, right?
Yeah.
In your thin layer experiments, in your thin layer setup.
Thin layer, that's an analytical solution. We didn't consider that effect. But you are right, it may.
So thin, and then you press so fast, because it's incompressible, there should be bulging out somewhere.
So.
It depends if the fluid doesn't go out,
Yeah.
No,
it has
that's
to go up.
that's dynamic.
That's basically my question.
That's dynamic behavior. We don't simulate dynamic behavior.
But for getting the instantaneous response, you need that dynamic, right? In poroelasticity, you get it
Yeah.
from the instantaneous.
In the instantaneous data, we don't, in simulation, we don't consider dynamic. The way that we do it is we constrain the diffusion. So let the material, not allow the material to diffuse in the first state. And it's really like you compress an elastic material, right?
So you just set up?
We don't discuss the loading rate effect. So it's really like the Hertzin contact problem. You compress the material elastically, right?
Thank you very much. It's a good topic for lunch.
Sure.